Um, Welcome. My name is Sander, and this is some work I would like to show to you in collaboration with Nick, who works for Meta. And if you are not completely up to date, that's the former Facebook. And I am currently at RWTH Aachen. So let's get started. Process mining. I assume you all know what that is. But in a nutshell, there is a process running. We do not know exactly what it looked like, but we have an event log that is being recorded from it, and we want to know something about this process. So we only have this event log. My focus of today will be causal reasoning, and a very famous example of causal reasoning is the ice cream versus drowning. So from data, it has for a long time been shown that the more ice creams are sold, the more people drown on the beach. So hence, we can conclude that the sale of ice cream causes drowning. Well, obviously, this is rubbish, but this is one of the common things that are currently, well, in basically most of the process mining techniques that we know. You are looking at correlations, not at causation. So correlation does not imply causation. And when I say causation for this talk, I do not mean the directly follows relations from the alpha miner. I mean causal inference, the mathematical field. Okay, so causal reasoning in process mining. Am I the first to do that? Or are we the first to do that? No, of course not. There have been several approaches. So for instance, can we intervene in a process in order to optimize a cycle time or to make an SLA? That has been done in a causal way. Similarly to influence the likelihood of a particular outcome. And kind of retroactively, that's also causal analysis, is if there was a negative outcome, can we explain why that negative outcome was reached? Well, of course, we love this this direction. So we think that this is, well, yesterday I had a chat with somebody, and I'm gonna quote him. It's a bit of the holy grail of process mining. How can we move on from purely associational or correlational things to causality? But we're gonna take these approaches one step further. And we do that using process models. So let's say that we have a process model with two decisions. In the front, we have a decision after A between B and C, and then a little bit later in the process, we have a decision between E and F after D. Now, what we want to be able to express is that increasing the likelihood of B causes an increase in likelihood of E. So notice that this is not a correlational statement. This is a causal statement, because we influence B and then something happens. Well, if you only have correlation, you have no clue what's going to happen to E. So we want to make a statement along those lines. We also introduce a term for it. We call them causal soft long distance dependencies, because we are looking at decisions between processes, so hence the long distance. And it is soft because, well, regular long distances are modeled in a very hard way. So you can either, you completely cross out options. That would be a hard long distance dependency, but we look at soft long distance dependencies. So dependencies in terms of something makes something else more likely. And of course we want causal and not correlational. What can we do with that information? Why would we want to do that? Well, for instance, we can inform interventions within the process. So if we are running through the process and in the end we want to increase the likelihood of transition E, for instance, make a sale, then once we had the decision between B and C, using causal soft long distance dependencies, we can already steer the process towards E while we're just doing B yet. So we could increase the likelihood of B. And of course, if you're redesigning a process, then such causal information is also very valuable, because it allows you to do that on a whole process scale rather than a trace scale. So we need process models, and for this work, we considered process trees and directly follows models. This is an example of a process tree, and if you have not seen it before, you start in green and you walk to red, and just along the edges, and every box is an activity that you execute. So the language of this thing is, well, you can do C and then E, D, E, D, F, and so on. But, well, the kind of more interesting part is on the top. We have a loop between A and B. So if you choose to go for the loop, you do an A and then you have a choice. Do I finish or do I do a B and an A and then I'm in the same choice again? So that is a loop. We can identify choices because we're going to talk about choices, causal reasoning over choices. So what are the choices in this process tree? We have one at the start of the process where we can go up to the loop, in the middle to C or the bottom to D. We have a second choice at the end of the loop where we can, well, exit or continue to the loop again. And at the end we have a choice between E and F. These are the choices in this model. Now a little bit more about causal reasoning. How does it work? And actually this will become clear, I hope, at the end of the talk, but to get started, what we need is a causal graph to denote relationships between the choices that we have. So in general, a causal graph, the nodes are our decision variables and the edges denote there might be a causal relation here. So if I show you a causal graph, then you should not be thinking, oh, there is an edge, but rather, oh, there is no edge there, because that gives you information that says there is no causal relation here. So for instance, if we want to express the causal influence of a variable x on a variable y, so these are just standard decision variables, well, that's still rather easy. Where it gets more interesting if different variables have the potential to influence this relation. So for instance, z here, that's a different decision variable, is called a confounding factor. So that means it has an influence on both x and y. This structure is called a collider. So x and y have a causal influence on u. And finally, a chain is, something that's kind of sits in the middle between x and y. So if we're looking at direct causal influence, we're just interested in the edge from x to y. If we're also interested in indirect causal influence, so how would you say that? X influences v and v influences y, and hence by transitivity x influences y. That is indirect causal. From such a graph, which denotes our knowledge of what causes what, we can, in some cases, derive the strength of these influences. So that is, in a nutshell, what we're going to do for process mining and process models. So our approach has a lot of steps, and we're just going to go through them one by one. So a causal graph is not directly derivable from data, obviously, because if you look at data, you just get correlations. So we need something else. Well, we're going to use the process model. So this is our model that we saw before, and our first job is to create a causal graph that is kind of the upper bound of the entire model. So what we're going to do is we're going to take the nodes of which are the choices in our model, and then we're gonna add edges that do not violate this model. So let's look at let's work out this example. The first choice the first decision in our process model is between doing the loop, doing C, or doing D. So that is our first node in our upper bound causal graph. Similarly, at the loop, we have a choice between doing the B and going through the loop again, or stopping, and let's denote that with tau. Now, a causal graph obviously cannot have cycles. So it cannot be that two things have a causal influence on each other. That is impossible. So how do we do that with loops? Well, the answer was there already. We unfold them. So rather than taking one choice of going through the loop again or exiting, we're gonna duplicate that. So let's say that we've done a B, then we end up in the same choice again, and that is, in the causal terms, a different choice. It's not the same choice anymore. So we need two nodes, and that goes on, because it's a loop, until you think it's enough. So for this, there's conceptually no reason to stop, but yeah, given that we're also working with logs, something that would make sense is just to take how often the choice was made in the log. Finally, we have a choice between E and F, and that are our nodes. Now we need to add the edges that do not violate the model. So, well, from the first choice between loop C and D, in principle, we could add just to everything, to all the other nodes. And in this case, that is true, because this choice between the loop C and D is the first choice, and everything else comes after it. So in principle, this node could influence all decisions after it, but not the other way around. Because this is the first choice, it is all the other choices come after it. So yeah, these choices cannot influence this first choice. So we have to add all all outgoing edges of loop CD. Next is the decisions within the loop. We have a similar argument. So the first decision in the loop influences all decisions after it, but not the other way around. So we can add that as well. And finally, between the nodes of the loop and the choice between E and F, we have a similar reasoning. It is sequential, so we just need to add all the edges. This is our upper bound causal graph. So again, this is a causal graph. It's not very limited yet, so it doesn't give much information. But what it is acyclic, and it contains all edges that are okay according to the model. So we've already ruled out everything that violates the model. Okay, next step is a bit of a technical one. We're gonna use standard causal reasoning techniques afterwards, and they cannot handle these three choice nodes that we had. So loop BC techniques cannot handle that. So we need to binarize that, if that's a word. So we need to split the nodes that consist of three options into binary nodes, and we do that as follows. So rather than choosing between loop C and D, we can choose, we can say we have one choice between doing the loop and not doing the loop. We have one choice between doing C and not doing C, and we have one choice between doing D and not doing D. These, of course, inherit the causal edges from the node that we started with, so that already gets a nice messy graph. But amongst them, notice that the model said that we chose between three options. So these three, if we separate these options, they were still decided at the same time. So there are no causal relations between them. So this is our final binary upper bound causal graph. Okay, next. In order to move further into the kind of standard setting of causal reasoning, we need data. And we have that in form of the event log. So what we're going to do is take our very small event log and replay that on the model and record which choices are being made. So let's just go through this example. The trace CF fits the model, so the alignment is not going to do anything special here. So the align trace CF, did we go through the loop or did we not go through the loop? Well, we did not go through the loop. Did we go for C or not C? We chose for C, and we did not choose for D. So this is a simple replay of the aligned trace on the model, recording the choices. But now something kind of shaky happens, and that is the choice between B and tau. We did not make a choice there, because the trace never got there. Well, this actually kept us busy for a good few months, and we, in the end, found a very recent technique that can handle this. And what we need is a tree-symbol logic. So, of course, that's not so special, but the causal reasoning technique that can handle that is special. So we have yes, no, or never encountered, kind of missing data. So the three loop choices were never encountered, and for EF, we chose F. One more example for the trace AE. The alignment will tell us that actually there was this loop exit in the middle, this tau. So if we translate that into the choices, then we saw that we took the loop and not C and not D. For B tau, we took the tau, and so on. Okay, this is the data for data about choices. We call it choice data, and this is an input for standard causal inference techniques that we now have. Or do we? Not yet, because we have an upper bound causal graph, but yeah, that's an upper bound. It doesn't give much information. So we need to do one more step before we can go into actually computing our causal effects, and that is to create a causal graph. So luckily, there are standardized techniques, and this is the magic technique from 2019 that we luckily found that can handle missing data. It's called MVPC, and what it gives us is a so-called Markov equivalent class. Notice that this is all data-based, and from theory we know that in most cases it is not possible to derive causal relations from data directly. So this technique can also not straightforwardly give us a causal graph in all cases. So rather it gives us a set of causal graphs. And let's pick our example. This could be a set of causal graphs that the MVPC algorithm would give us. So we see some edges are there, some are removed, which, remember, is what we want. That is the information. But yeah, some edges are not directed. It cannot go beyond the correlation yet. However, we have the model. So our upper bound causal graph that represents the information of the model is acyclic and gives direction to every causal graph that we got from the algorithm. So if we kind of project that onto each other and do a simple conjunction, then we end up with a causal graph that we can use. So now we have a causal graph. We have our choice data. Now it's finally time to get into the actual computation of the causal relations. And this is all standard techniques. This is of course not by us. How do we do that? How does it work? We have let's say that we are interested in one particular causal relation that we get from the causal graph between B tau and EF. What the causal model then says is that we need to do a linear regression, a simple linear regression between the choice of E and F and the choice of B and tau. So this is the most standard linear optimization problem that you can have. Okay. If we do this, I mean, we have the choice data. We know what came into this, so we can compute C1, C0, and C1. But that's not correct, right? Because we have this D not D, which is a confounding factor for B tau and EF. So what the causal graph tells us is that the decision between D and not D also influences E and F. So in order to kind of correct for that, because we want to take that out, we want to have the causal effect from B tau on EF, we need something called the backdoor criterion. And that is a technique, an existing technique that looks at the causal graph and tries to find a so-called adjustment set, which is simply a set of nodes that need to be taken into account in this linear regression. So in our case, this adjustment set would be D or not D, and we simply add that to the linear regression using, well, pretty standard extension, and then we can solve this linear regression. And what we want in the end is the parameter C1. So we want to know the influence of B tau on EF. This, what we then get, is called the average treatment effect. And what it means is you can increase the expected value or probability of b tau, so choose one, um, uh, by doing let's say that again. You can increase the likelihood of EF by doing b tau, and the amount of probability mass that you increase is C1. That's what this means. So, of course, there are a few drawbacks, and causal reasoning is a well-grounded thing in mathematical theory. The inventor got a Turing Award for it. So, but yeah, as with every model, there are some abstractions. So we need to conjecture, or basically hope, that from the conjunction with the upper bound causal graph, only one causal graph will remain, but that is not guaranteed. There might be multiple. Second, this backdoor criterion is not always successful. It doesn't always exist. So yeah, in our evaluation, this was not a problem, but theoretically it could be, or maybe it couldn't. We just didn't figure that one out yet. And of course, the standard assumptions, the model must denote the moments of choice correctly. If the choice is made before the model says it's made, then of course we cannot do anything. So we assume the choices are made at the time the model says. And this is also a pretty standard assumption, but of course, kind of an umbrella assumption. Everything that influences the variables you're looking at is included in the causal graph, or in our case, we only use model decisions. So no unmodeled confounding factors. So to give you an example of the things that an end user might get from our technique. Skipping, so this is from our actual evaluation, the BPI Challenge 2012 logs. It has passed by already quite a few times. So what we found for this one is the first time that you do the choice that is called O1, if you then skip O cancelled, then the next time you get to that same choice, the likelihood of doing O cancelled decreases by 0.62. So that is 62% less likely to happen in the second choice, in the second run. We'd also tested it on 5 real-life logs and 2 discovery techniques. Of course, we do not have a way to verify that what we find is actually correct, but just some numbers. We had up to 288 choices, up to 24,000 edges, and in the end, so after our technique was done, 0 to 7 edges, and we are actually quite glad with that result, because that means that the user is not being flooded with causal information, but even though you have this massive opportunity for causal, it still finds just a few. And runtime is, quite good, especially when you say, when I remind you that we need alignments to run this. So, kind of conclusion from this experiment, the causal relations are there and we can compute them. It is feasible. We didn't use any supercomputer or anything, just standard hardware, and the user is not flooded with these causal information, at least for our examples. So what I've shown you today is a new way to combine process mining with causal analysis, and I hope this will trigger other people to also look into this field, because we agree it's by far not done yet. We did it for process trees and directly follows models. For Petri nets, it's going to be a different ballgame, because of you need to really know the structure. First, you create an upper bound causal graph, then you make it binary, you record the choice data, construct a causal graph, and then in the end you do a standard regression. So some gaps is how to visualize and explain this. We thought it would be trivial. It seems it's not. I mean, we split these nodes, and then you have to kind of get back to 3-level choices. And this linear probability is additive. So this model says you add 62 to the probability, and that means that it might go above 0 or even below 1, above 1 or below 0. So it's a bit shaky, but that's what's standard in economics. So future work includes getting more confounding factors from event data. We would like to do it on PetriNet, and in the end perform a case study to truly validate that this all holds. Thank you. I think press it. Now it's off. Yeah, just let it go now. Yeah, I think it should be good now.
No? It's okay. So,
thank you. What kind of algorithms have you used getting from the first graph you had to the acyclic directed graph? Did you use any special algorithms, or did you implement your algorithms?
Which
from the first node, from your initial cyclic graph to...
so our initial graph is already not cyclic. So the upper bound causal graph is acyclic already.
Okay.
So we use that to kind of prune the edges in the standard in the kind of causal graph class that the algorithm gives.
I thought you said you had a step that made it acyclic.
No, it is by construction.
Okay.
Yeah.
And I was gonna ask the complexity of that, because that's a big problem itself in my domain of mathematical sciences. That's why.
Yeah.
So if it's not...
Yeah, so in terms of complexity, of course, any graph has at most n squared edges. Mm-hmm. And yeah, constructing them on a process tree is just that's nothing, because you have the structure already. But where the difficulty is that you need to unfold the loop. There might be some complexity there, but that part I don't think anything non-polynomial is present. Don't shoot me.
Thanks for the nice talk. I had a small question about how you get to the binary causal graph.
Yeah.
So you split the node with 3 choices into 3 different choices, but you don't split the binary choices, or could you have also split the 3 choices into 2 choices between the loop and C or D, or how does it work?
Well, the short answer is we chose to do it this way, but yeah, it was more of a kind of a funneling, like engineering step in order to make that we could use existing causal reasoning techniques. I mean, I don't see any way why you. I mean, I modeled this using 3 choices, but I can very well imagine that you could do it in 2 in order to optimize that. Yes. Yeah.
Okay. Thank you.
Thanks, Anders. Very, very interesting. So you already mentioned, right, that you would like to lift this to PetriNet, right? Can you maybe comment a bit more how could you incorporate here some stochastic knowledge about the data or about the process model? Because I think this would naturally fit, right, since this framework naturally handles probabilities in a way.
So
but
let
maybe a
me break that up
tricky...
in 2 parts. So first, the PetriNets. I mean, there is no conceptual reason why you couldn't do this trick with the upper bound causal graph on a PetriNet. It's just that it's just much harder, because in a process tree, I know, like I have to, I mean, in the paper, it's a recursive call, so that's much easier to do. Well, in a standard or in a general PetriNet, you would probably have to do a full state space exploration. But kind of the tricky part is where to start the next unfolding of the loop. So in a process tree, again, that is very easy. In a directly follows model, it's a bit harder. And a Petri net has even less structure because you have things like concurrency, how you're going to do that. So yeah, all these things will. My conjecture is that is possible. We just didn't do it yet. But yeah, there are some things underwater that you need to solve, but I think it's doable. For your second part, well, actually the choices that we have here in the model, what we are saying is how does the stochastic perspective change based on the choices that you make. So if you make a choice at the start of the model, then how does it influence a choice later in the model? And that is the stochastic perspective. However, I would not really know how to include the basic stochastic perspective in that, but kind of it's a bit orthogonal because this tells you how the stochastic perspective changed, but like the original stochastic perspective, right? You can just combine that in the output and then kind of interpret them at the same time. So yeah, my initial like low-hanging fruit answer would be that it is something that you could consider like in a user tool or something, or when we finally get this user accessible, then yeah, that you can there use that combination.
Thank you for a nice presentation. I was just wondering whether the choice of the model representation was intentional or not. So like the first thing that I'm considering is that, well, you're having a direct follows relation there, but you could also use a declarative model like declare or the like to start from the to start your analysis. And declarative models are more close to causal relations than DFGs. So I was just wondering why did you choose what you choose?
Well, the process trees was an obvious. So why? So again, two things: why process trees and directly follows models, and second, why not declare? So why process trees? Because they are by far the easiest. They for this kind of work. They are. You can write a recursive definition and it just works. That's it. So the only complexity there is to unfold the loop. And in a process tree, it is trivial to know when you get into the next loop. So that was the first one. But then we said, yeah, process trees, CAiSE', we need something else. So then for directly follows models, they are still kind of structured, and the state space is nicely, let's say, yeah, it's nicely structured. So it's one token just moving through the net. So in the sense of detecting when you enter the next loop, that's, yeah, we needed to do some work to detect that and to reduce that in order to not blow up everything after that. So that was kind of the second choice. So short answer, pragmatism. Why not declare yet? I think declare would also work. However, please note that what we need is an explicit representation of the choices. So in a Petri net, that is already a bit more difficult because of all kinds of unbounded places and that kind of thing. But in declare, a choice is, well, the whole idea of the declare language is that you do not have explicit choices. You have now, you even have constraints that might not hold yet, but can still hold. So in terms of, yeah, of getting the choices out of a declare model, I think it's even more challenging than Petri nets, because yeah, you would have to construct a whole state space and then explicitly and then say, okay, I have this choice, I have this choice, I have this choice, and then yeah, all the kind of the elegance of the because right now I could say this choice has an influence on this choice, but if there are no choices in a declare model, I cannot even say that. So that I think, would it be technically possible? Absolutely. But in order to get that into something user-friendly is another step further. So challenge accepted.